Hi everyone, welcome to this new room for our reading groups. So I will speak about this paper called Neural Corroborative Filtering, which appeared in WWW conference 2017 by Xianyan and colleagues. Okay, so just a little bit about the type of data we are interested in when we talk about collaborative filtering. Is basically some form of user-item interactions. This can be ratings, clicks, or just like binary feedbacks like, dislike, etc. So our objective is to try to predict the unknown user-item interactions, and then eventually use the scores to make recommendation for users or to rank items. So we are probably more familiar with the word recommender system, but basically collaborative filtering is an important component or an important family of recommender systems that mainly work with this type of data like user item interactions. Okay, so the famous collaborative filtering model, or the most popular in practice, is perhaps matrix factorization. So the idea is simple. We have our feedback matrix Y, and we try to decompose it into two latent matrices, one that represent user factors or user representations, noted here P, and the other one that represent the item factors, we call here Q. So the idea is that we feed this matrix to the observed user item interactions, then subsequently we can use it to predict unknown ratings, and then we can rank items based on the scores. Okay, so formally we can view it as using a function that will try to explain the original ratings. Of course, we cannot recover the original matrix exactly, so we will just approximate it. So I use this notation here, F, to denote the scalar product, because it would make it very easy to understand what a neural corroborative filtering did actually to extend this framework. So here I assume that P and Q are low rank matrices. Here U is the number of users, and I is the number of items, and K is the latent dimension of your user and item factors. Okay, so this is NCF, or neural corroborative filtering. So basically, what is NCF? NCF extends matrix factorization by using a neural network to combine the embedding matrices P and Q. So previously, F, the function F was the scalar product. Now F is replaced by a neural network, or MLP. So the idea here in this diagram is that first we have every user is represented by a one-hot vector, and every item is represented by another one-hot vector. So the first operation, you can think of it as just selecting the embedding of the corresponding user. So remember, we have our matrix P and the matrix Q. So this first operation here, for example, for a given user, would select the corresponding embedding, actually. So this operation would select the appropriate factors for every user and items. Then we just combine them using some neural network. So basically, we replace our function here with an MLP. Previously, we used a scalar product operation. Then at the end, we have the output, which is the score or the prediction that approximates the user item feedback. So this is the main change, actually. You have scalar product, you put the neural network instead. Okay, now, so there is this variant the author called generalized matrix factorization. So what basically is generalized matrix factorization is just actually the author highlighted we can recover MF by taking or restricting the structure of this MLP. So basically we just need to pick one layer, which is the pointwise multiplication. Like after you have the user and item embeddings, you take this layer to be the pointwise product. Then you take another layer, basically the output layer, which is actually just the scalar product between this H1 and this H2, which is a vector containing all one. So this operation actually is just another representation for the scalar product I showed you before, actually. Yeah. So they call this one GMF in the paper. Okay, then we come to neural matrix factorization. So what is neural matrix factorization is the fusion of the two approaches that we saw. So here they combine both the GMF layer, which acts as the normal matrix factorization, and the MLP version of the null corroborative filtering. Now, it's not exactly the matrix factorization here, because at the end we just get the representation, which is the element-wise product between user and item embeddings. Then we combine them with another null layer here. Okay, so the whole idea here is just like you have user and item embeddings, then you can basically use whatever function that can combine them actually to provide you with a score that you can later on optimize to be close to the original or the observed ratings. All right, experiments. The models have been evaluated on two datasets, MovieLens 1 million and Pinterest. Okay, so the evaluation metrics will be NDCG and the hit ratio, which is basically here just recalled because they use leave one out. So basically this HR, you can think of it as recall actually. And then the baselines are Bayesian personalized ranking. I think the one-to-one will be presenting. Item popularity is just a collaborative filtering that recommends the most popular items. Item canon is the recommender system that use the neighbors of the items that some user have enjoyed in the past to make recommendation. And then EALS is basically just some form of weighted matrix factorization. So here, weighted matrix factorization depends like on the way they observe the importance they give to the observed ratings and the missing one or the unobserved one. Okay, so the main results are as follows. So the main points here is if we look at the MLP version, which is the very first NCF that I introduced, it actually doesn't perform that well actually. And at some point actually here we report for different predictive factors. So the predictive factor is the last hidden layer before making predictions. So we can observe that sometimes this MLP may be actually outperformed by other approaches like the EALS version. But however, if we look at the GMF as well, which is basically matrix factorization, it also performs provides very competitive performance as compared to the MLP version actually, which actually highlights that this matrix factorization framework is still very strong actually for recommendation. But the combination of both approach, which is the neural MF, seems actually to stand on the top in terms of performance across different scenarios. Okay. The authors also investigated the impact of pre-training for neural MF. So remember that neural MF is composed of two main components. We have a matrix factorization component and the MLP component to combine the embeddings. So neural MF combines both approaches. So the pre-training here means we first train the MF part, and then we train the MLP part separately. Then we use them to initialize the whole neural MF framework actually. So the authors show also the results here show that using pre-training can help to improve performance most of the time, which also emphasize the difficulty of training such architectures, especially on sparse datasets like collaborative featuring one. Okay, it's a bit hard to compare actually, but basically you need to look at this column and this one and this column and this one. So most of the time pre-training actually, except for the first case, helps quite a lot, especially when we increase the capacity of the network. Okay, now this experiment or these results show the impact of the number of layers. So here is only for the MLP version. The MLP version, or what we call NCF, that the very first diagram that I show, so they test with different number of MLPs. So in the main experiments, they report the result for a 3-layer MLP. So here they investigate different number of layers, and it seems like using more layers tend to help, at least up to 3 layers, because mainly after we reach 3 layers, from 3 to 4, we don't notice a very huge difference most of the time. And actually, I doubt that is statistically significant in most cases. So it seems like up to 3 MLP seems to be reasonable. More than that, you will probably just increase the complexity of your model without gaining too much performance. So that's all. Thank you.